as you can see, I wrote down a lot of derivations on the blackboard. Not a lot, only 3 lines, but if you have time, you can just write down for now. So, as I said, the focus for the next 15 minutes is only on one thing: reaching impedance matching. Because when we have a matched line, we can deliver the maximum amount of power to it. So there are 2 ways to do it. I won't go into the details for now. I will talk about the general consideration. Right. So usually, we have a transmission line, we have a generator, and we have the load. It will be very difficult for the load to really match to the transmission line. It's in our dream, but it's really not possible, always. Okay? So let's take a look at the load impedance. A load impedance can be separated into 2 parts. The first one is the real part, the resistor. Second part is the imaginary part, right? Capacitors or inductors. So in any case, the impedance is a complex number. It will have its real part and its imaginary part. And since the very reason we want to assume the transmission line is lossless is the characteristic impedance in this case will be purely real. Okay? So think about it. We have a load. It's a general load. The resistor value can be anything. Imaginary value can be anything. And now our goal, our target, is to say that the load impedance would be matched to this. Z0 for a lossless transmission line is purely real. So then you have to ask yourself, is it possible? Impedance matching means the load impedance ZL is equal to Z0. But Z0 is a purely real number. So there's no way, in general, to reach impedance matching. Okay? So we can only hope for by hope, let's do this. We can hope that somehow, okay, through the knowledge, we have RL plus JXL and somehow transformed over a distance d, right? You still remember, we defined the wave impedance. So which means I start with a load, I know my load, I walk for a certain distance, I look into the right, that's my input impedance. So the input impedance, we know, can vary as a function of distance, right? But usually, the wave impedance is also a complex number. So now, after I walk for a certain distance, I look at the input impedance. It's RS plus JXS. Or let me say D. What am I using? Okay, D. I'm using D to denote the resistor value and the imaginary value, reactance value, are both a function of distance. Okay? So somehow I converted the problem to this one. Initially, I have my load, which is a fixed value in terms of the real part and imaginary part. But something I learned in the past 15 minutes, I know that if I walk on the transmission line, and that transmission line segment plus the load will convert into a new impedance. And that new impedance is changeable, right? So even though in the case RL is not equal to Z0, remember again, this is real for a lossless line, right? So even in the case, my starting point is my load resistor value is not equal to the characteristic impedance of my transmission line. I have some kind of hope. By walking for a certain distance on the transmission line, and I look at the transmission line together with my load, somehow, potentially, RD is equal to 0, Z0. Right? Then I have a very good starting point to achieve impedance matching. So think about it. Do you understand my philosophy up to now? The load itself is not matched to the transmission line. But what I can do is, by walking for a certain distance, then I'm using the effective ZD, right? I'm combining the load and a segment of the transmission line to function as an effective impedance. And then I know I can change the values in the real part and the imaginary part. So let me write explicitly for you. These are both functions of distance. So it's changeable, tunable. So you might be able to find the right distance where the real part is magically equal to the characteristic impedance. So at least the real part is matched. But then in this case, XD, what happens to XD? XD is the imaginary part to your wave impedance. We want to kill it, right? Why do you want to kill it? Because by impedance matching for a lossless transmission line, the characteristic impedance is what to be matched. It only has a real part, so we need to eliminate the imaginary part of the wave impedance, right? So this is the overall goal. Our overall goal is to find the right position on the transmission line, including the load impedance, and at that position, the real part of the wave impedance is matched to the characteristic impedance of the transmission line, and somehow you cannot just pray for this condition to happen. Okay, this is something artificially we have to manipulate. We have to do something else. Okay? So are we clear up to now? Then it's the next PowerPoint page. Okay? So this is what we're going to do. This is what we're going to do. I'll explain what we are going to do and then again, and then go to the blackboard. All right. Think about how to kill or eliminate, if you don't like the word kill, how to eliminate or remove the imaginary part of the wave impedance. We have a load, we have a transmission line with the right distance, right? The way we want to perform impedance matching is we don't want to cut anything. Okay? At least we don't want to cut the transmission line. Assume the transmission line is already connected to the load. Wouldn't it be better if the impedance matching could be performed in a non-destructive way? 非破坏性. We don't harm anything. So at this distance, I already know that the real part of the wave impedance is matched to the characteristic impedance of my transmission line. All I have to do is kill the imaginary part. How to kill the imaginary part? Or what do I mean by killing the imaginary part? If the imaginary part of the wave impedance is positive, it means you are having an effective inductor, right? So you have a positive imaginary value. And then we can connect what? A capacitor in parallel to it, right? To make the imaginary part going to zero. Why? Capacitor will give you a negative imaginary part in terms of its impedance. Okay? So we're working everything in parallel. Because working in parallel, we don't have to cut anything. We don't need to cut the transmission line. And therefore, it's a non-destructive way. Right? Since we're working everything in parallel, we want to convert everything into the admittance. Admittance. Okay. So now I'm showing you the input, the load admittance is the inverse of the load impedance. Admittance is just divided by 1 over the ZL. Okay? So everything is now working in parallel. So let's go to the blackboard. So when everything is working in parallel, 1 over Z total is 1 over Z0 plus right? Everything. I'm trying to explain why I want to use admittance, because when you have something working in parallel, you have to add the reverse, right? Reverse adding reverse equals reverse. This is very tedious, so why not just use admittance? Y0 plus YD, right? Admittance, you add them directly. Okay, so now, what is my general philosophy? I know somehow, right? Starting with my load admittance, I walk for a certain distance, I will arrive at my effective wave admittance, YD. Okay? YD is still complex. It still has a real part and imaginary part. But somehow I can kill the imaginary part by shunting. Shunting means connecting something in parallel, shunting, to remove the imaginary part. Okay? So, YD the wave admittance is also having the real part and imaginary part. Okay? So my goal is, oh, this is tedious. Okay. How should I write it? Yes. Okay. So let me remove this one. So what I'm trying to do is, YD is the admittance of the load plus a segment of transmission line. Then I want to connect something in parallel, which is purely imaginary. So this Y total would be GD plus J, BD plus BS. Okay, clear? Because I'm connecting something in parallel, which is purely imaginary, so I only add the imaginary parts together. So GD is the inverse of Z0, and BS is equal to, I have a special way of writing it. Negative BS would be BE. Okay? So this is my overall target. By connecting a purely imaginary component, maybe a capacitor or an inductor, at the distance of d, what I'm trying to do is I want to kill this term. Right? I want to kill that. So I only have the real part remaining, and at that distance, the real part of the impedance is Z0, matching to the transmission line. All right, so let's go. Where should I start? I'm still starting from what we learned last class, the wave impedance. The wave impedance is defined by the total voltage phasor divided by the total current phasor. Okay? So now, remember, the reflection coefficient is usually itself a complex number, so I'm writing it as an amplitude with a phase. Okay? For simplicity, I am going to call this theta gamma, which is the angle of the reflection coefficient, minus 2 beta d as theta prime. This is for simplicity. So now we have the simplified formula for ZD, the wave impedance. I can invert it. I invert it, it becomes the wave admittance, YD, okay? Admittance. It's just flipped. What I'm trying to do now is to rationalize it. 有理化, rationalize, right? I have 1 plus gamma v, absolute value, exponential j theta prime. I want to rationalize it, so I don't have this exponential terms anymore. I'm multiplying the same thing on top and bottom. This is called rationalize. After all the manipulation, you will have the picture file. The TA took the picture already. Okay? So you will have the real part and the imaginary part. So this is the front part is my GD. The second part, multiplied by this, is my BD. Alright, so this is summarized here for you. I merely copied what we had on the blackboard. So now I'm isolating the terms. So the real part of the wave admittance is this form, and the imaginary part, okay, of the wave admittance is written in this form. So now we have to solve. How to solve it? The easier one, now we have two equations, right? We have two equations. What things are we trying to solve? Eventually, here, the characteristic impedance is given. So this is known. Reflection coefficient, known. The only thing unknown is theta prime. Okay? So actually, with only one unknown, there's no need for two equations. Right? So we can actually know theta prime just from this single equation. 1 over z0 equals 1 over z0 multiplied by this. This is 1. Okay. So this converts into 1 plus gamma v squared plus 2 v cosine theta prime is equal to 1 minus v absolute value squared. So you kill the 1. From this very simple equation, it immediately tells us the only remaining parameter to be solved is so easy. Once you know your voltage reflection coefficient, you take its absolute value, take its negative, and you have theta. Straightforward. Meaning, impedance matching is not very difficult. Once you know how unwell it is matched, or how big it is mismatched, you know how to fix it. Okay? But at this point, straight on, let me ask you this question. Is that cosine solution a valid solution? Cosine theta prime equals to the negative of an absolute value. So cosine is negative. Is it valid? Cosine values usually are smaller than 1, greater than negative 1. So is it still valid? So this is a point to your understanding. How big is gamma v swinging? Gamma v is, again, limited to below 1 and above negative 1. Right? So this is valid. So this is okay, because this absolute value is bounded by negative 1 and 1. That's basically this absolute value is above 0 and 1, so it's okay. And then you have to think, this is the critical point. How many choices do you have to accomplish impedance matching? Cosine. This is the absolute value, so cosine theta prime must be negative. So cosine takes on positive values in the first and fourth quadrants, and positive in second and third quadrants. So this means for every impedance matching problem, you always have two solutions. So you always have you will have two choices of theta primes. For each theta prime, do you still remember how theta prime is defined? No. Theta prime is defined by the reflection coefficient angle minus 2 beta d. So it means for each theta prime you derived, you have a corresponding magical distance. So theta prime comes in with a pair. Try to pair up with a right distance. Okay? So remember, whenever professors are asking you to perform impedance matching, he's trying to trick you. There are two potential choices. At location 1, you have to connect certain imaginary part, right? And there's another location where you can connect another type of imaginary component. Okay, remember, two choices, two distances. Okay, so under this condition, since cosine theta prime is negative absolute value of gamma v, this can be simplified, right? So let's try to simplify this. So this is negative 1 z0 times 2 gamma v sine theta prime 1 minus gamma v squared. Do you see what I'm trying to do? So this is negative gamma v, right? Did I write it wrong? I think I wrote it wrong. Square is getting here. Okay? So this thing is becoming negative 2 gamma v absolute value squared. Right? So you have 1 minus only 1 gamma v absolute value squared.